All right, reflection of sound waves, section 11.7, page 360 in your Heath physics text, if you're following along. You are likely familiar with how a mirror works. So we're going to be talking about light a lot in the next sort of next sections, next chapters, after chapter 12. 13 to 16, I think, is all about light, reflection, refraction, colors, all that sort of stuff. But now we're still dealing with sound. But you are familiar with how a mirror works, right? The light bounces off the mirror. The angle that the light hits the mirror is equal to the angle that the light reflects off the mirror. All right? So the reason why you look in the mirror the same way you actually look in real life is because all of those light rays are reflecting off of yourself to the mirror and then back to your eye. Okay? And they're all traveling in real straight lines. Now, if the mirror is polished and a beautiful mirror, you'll see exactly yourself. If it's like a rough mirror or textured or something, you'll see like a vague sort of outline of yourself. That's because the light rays that are coming from you, bouncing off of you to the mirror, are not being bounced back predictably. So if the mirror is not a good one, if it's warped, if it bends like that, then the light rays are not coming all parallel. They're going off in different directions, and you see something that's a little bit warped. But if we're talking about sound waves work in a very similar way to that of light. Okay? So you should be filling your sheet in here with light as your first blank. The sound can reflect off a flat surface. Okay? And I mentioned the other day about my Bluetooth speaker in my kitchen. I kind of turn my little Bluetooth speaker when I'm listening to, when we're in the kitchen or eating. I turn it, shh, guys, please no talking. I turn it so that it faces the wall over there because the sound will bounce off the wall kind of into the area where we're all sitting or eating or working in the kitchen. And the room is filled with kind of better quality music if I can aim it at that one flat wall so that the sound bounces off of that wall. If I face it into the cupboards or whatever, it doesn't get reflected very well. It gets muffled if you're anywhere else in the kitchen. So, you kind of think about that. Now, if it hits at a 90-degree angle, it reflects straight back. So if we have a flat wall, and the sound waves are coming in here, and exactly at 90 degrees right here, they're coming in there, hit the wall, they will bounce back exactly on the same path, just like light. If it hits on an angle, it'll bounce off at the same angle. So let's say it comes in, I should move that. Let's say it comes in, here's the wall. Let's say it comes in at this angle right here. Well, any of these angles that you measure, this one or with the perpendicular, this one here, it will, the resulting reflected wave will be at the exact same angle. Okay, so those will all be the same. And you kind of know how that works if you've ever played pool before, billiards. The ball bounces off the bank there, and it's always a predictable, reflection there, really. Okay? All right. The sound wave that bounces back to the source. So if we're thinking about this 90-degree situation here, I'll draw it over here. You can see it. But if we have a sound wave that bounces back to the, whatever the person or whatever is making that, if the sound wave that bounces back, that's called an echo, right? And so you can hear an echo in lots of different situations. Usually, if you're, in an open space, maybe at a quiet open space, if you're climbing, if you're in the mountains or something, or if you're, I don't know, if you've got a rock face beside you, you're out in the wilderness, and you shout, you can hear your voice come back, right? Or if you're in between two buildings in a quiet night, you can shout, and you can hear an echo, a slight echo back. So that's the sound waves bouncing back to the observer. Reflected sound waves can be used in a number of devices. So for example, sonar, S-O-N-A-R, bounces sound waves off of objects underwater. It listens for the echo and uses a computer to draw an image of what's in the water. All right, so have you guys heard of sonar before? Sonar in boats? So if you have like a ship or whatever, right? Here's your ship, and here's the bottom of the ocean or the lake or whatever. And let's say this ship is sending down, sonar sound waves as it passes maybe some object down there. So what's going to happen is the boat's going to send off this sound wave. It's going to bounce back up to the boat, and the computer, generates, what happens to the time, and all this sort of stuff bounces back, the time it takes to bounce back up and stuff like that. And so the computer goes and it draws, all these things it draws that you have something like this at the bottom, okay? So you have some kind of like boat or whatever, that's sunk or whatever. They can find things at the bottom. You can see other ships. You can see fish. A fish finder is the same way. You got this collection of, reflections. A fish finder is kind of the same way. Or a depth finder in a boat. If you have a depth finder, that's what it's doing. It's kind of mapping off the bottom. So if the bottom of the lake or whatever gets shallow, your boat will be able to determine that as it goes. It just kind of measures, the depth, and then can display that. Any questions? Okay. So sonar. All right. A parabolic microphone. I think we've talked about this in this class too, I think. If not, a parabolic microphone, yes, that's the shape of a parabola. So those of you that remember that word from math. The great use of a parabola is in reflection of light or sound. Any sound waves that are coming in from a distance and that actually intercept or are reflected off of the parabolic dish, they will all be reflected to some focus point here. And so that's a predictable reflection, and that will cause all of these sound waves to come to one point, wherever that, I guess, is. Let's say it's out here a bit. And so that's why it will collect a lot of sound from a very small space, and these will be magnified into the microphone. So if it was just your ear, right? So here's your ear on the side of your head there, right? Then you're getting a few sound waves kind of collected into your ear and going down into your middle ear there, your inner ear. But if you had a parabola or a parabolic microphone, a dish, then you could collect, many more sound waves, and the sound would then be sort of amplified, right? Just in the same way, if someone's talking and you go like this, you can actually hear better. You can hear yourself when you talk better. It makes things louder just by doing this. But also, if you just do this right now, you'd be able to hear me louder and a little more clear, because your hands would be roughly in the shape of a parabola, and you'd be collecting more sound waves. So I know no one wants to do this because you look like Dumbo or something, but you should try it once in a while to see if you can hear me a little bit better. All right. Okay. Any questions there so far? 11.7 or 11.7. This unit is technically unit 3, I guess, is why they have 3.7 here, but I'm using the textbooks there. So 11.8 is a bit on acoustics. We're not going to get too deep into acoustics, but I would like you to show you a couple, one or two of these videos today here. We'll just kind of see. So I'll have these up on the website. If you're looking at this video, I won't show you on this exact video here. But we'll watch these two videos and we'll find out the difference between echo and reverb and stuff like that. Okay, so the difference between echo and reverb, just watched on the video there. And just once again, the echo is the exact same sound sort of coming back to the observer. Reverberation is sort of like multiple copies of the same sound that come back and overlap to exhibit or to replicate some sort of natural open space sound. All right, so there's a difference between echo and reverb, and you can watch those videos again if you need to. So let's take a look at 3.8, which is a section 11.9 in your textbook on page 365. Given that we live in Saskatchewan, you've most likely noticed that sound seems to carry further in the winter. I don't know if this is something that you could pinpoint in your life right now, but in the winter, I don't know if you're walking in the, let's say in the woods in the winter, when it's really nice and quiet, it seems like you can hear sounds from a lot longer away, or more sensitive sounds, snapping of tree branches, stuff like that. In the winter, seems to be more crisp and carry a little bit further. This is not your imagination, it actually does. There's good reason for this, and it's called refraction. Okay, so there's a difference between reflection with an L and refraction with an R. Those are different. It's not just one person, making a mistake or having some kind of speech impediment. They're actually two different words. You might not know the difference between them, but that's what I'm here to explain. So refraction is a bending of a wave. This happens with light. It also happens with sound and other waves. But it's a bending of the wave. A reflection is a bouncing off of the wave where there's no sort of bending or warping. It's just a straight bounce. refraction is actually a bending of a wave. So when a wave passes into a new medium that conducts sounds at different rates, we get refraction. Okay. So we'll talk about this with light a lot coming up in chapters 13 to 16, I believe. But with sound, if you're talking or there's some kind of sound and you have sound traveling through air, then you have sound traveling through water, obviously that's going to get warped a bit, right? You maybe noticed that. Or if a sound coming out from the water, you hear this muffled sound, and it's different than if a person was just talking to you in the air. But in this case, different mediums can be the same type of medium but at different temperatures. So air temperature has a great effect on the speed of sound, as we've already learned, right? Speed of sound in air is affected by the temperature, 332 meters per second plus 0.6 times whatever times the temperature is, right? And so it can be less than 332 if it's really cold, can be greater than 332 if it's really warm. And so the result of air passing through unevenly heated air cause sounds to bend in a new direction. So the air temperature, a great effect on the speed of sound, fill in your blanks there. Okay, so if air is not evenly heated, it can cause a warping or a bend of the sound wave. As sound passes into cooler air, it slows down, bending into the cooler air. And we have diagrams here coming up, so I'll show you that in a second. But as it passes into hotter air, it speeds up and it bends away from the hotter air. Now this whole bending, how it bends into and away from, is brand new. We're going to start talking about it now. Also with light, it becomes a little bit more obvious. There's more diagrams, and we do more calculations with light, how that refracts into different media. But it applies to sound, so this is your first kind of look at it. In the winter, the ground is colder than the air above it. Because of the snow and stuff, it's cold near the ground. The air is a little bit warmer because the sun comes and heats up the air first, and the snow keeps the ground pretty cold. So the winter, the ground is colder. This creates a cold layer of air near the ground. And this causes sound to bend down towards the ground. Okay, so I have some diagrams below here. I don't know if those are on your notes, so I will get to those in a second. Let's just keep going with the notes here. So if the sound bends down towards the ground, the sound then bounces off the ground and keeps kind of going along this bouncing pattern. So I have two diagrams here, and here's the cold air one. This is winter, okay? This is winter. And what happens is this person that's talking, okay, we have cold air down near the ground. So down here is the colder air. This is cold. And sound, as the waves kind of travel, they almost get like pulled into the cold air. So instead of like going straight like this sound, and I'll try and zoom in a bit here. Okay. But the sound waves here, and you can see by this red arrow, the sound waves kind of get pulled in towards the cold air. And what happens is all of these sound waves kind of get reflected, okay? And bent down again towards and they kind of keep going on in this sort of pattern. And so you have sound that keeps propagating here. And so there's lots of sound where we are able to hear it. So it kind of gets bent towards, it bounces off the snow, it comes up and bends down, bounces off the snow again. So it kind of keeps rolling on. In the summer, different than this, we have really warm air near the ground because the ground, heats up and it's cooler as you go up. And so what happens is these sound waves actually get pulled into the cooler air that's above the observer, and they kind of get drawn up like this, and there's nothing for it to bounce off of, so they kind of get lost. The sound waves kind of get lost in the summer. So in the summer, the ground is warmer than the air above it. There's a hot layer near the ground. This causes sound to bend up towards the sky, and then never to return. There's nothing to bounce off of. This is why sound does not carry well on a hot day. And also because of wind and stuff too. It's usually quite a bit windier in the summer, which affects the sound waves and kind of tosses them about. But this is our first look at something called refraction, the bending of sound waves. And when sound travels slower in a medium, at the barrier of that medium, the sound wave that kind of comes down will kind of get pulled down. Let me give you another example. I don't know if this is coming or not. Nope. So another example over here. Let's say I have a top view of a wagon, Okay, so you know those old wagons, like the old red wagon or whatever, and have the wheels like this. Okay, so this wagon is, you know, here's the handle, whatever, right? So it's going in this direction. Okay, and what's going to happen to this wagon? These wheels are free to move, right? They're free to move. Right now, this wagon is traveling on the cement, but over here is grass. Okay, I don't have a green marker at my ready here, but this is grass. And so this is pretty dense, okay, more dense than the cement. And so what's going to happen to this wagon, with the wheels that are free to move, what's going to happen to that as it hits the grass? It's going to what? This first tire is going to slow down quite a bit. It's going to get kind of almost caught in the grass. And so this wagon is actually going to end up to be sort of looking like this, because those wheels are going to turn into, right? They're going to turn into the grass. So it's going to go like this, and then as soon as it hits the corner here, it's going to bend this way. Okay? So it's tough to draw, but you know, it's coming down towards the grass, and then as soon as this wheel hits the grass, it kind of gets pulled in and it changes direction a bit. So that's what happens to the sound waves. Okay? Let's just finish up this section here if we can. So a few more minutes. Diffraction also deals with the bending of waves, but in the situation of traveling through an opening. So when you travel through an opening, the waves kind of like spread out like this. When a wave passes through a narrow opening, smaller than the wavelength, it spreads out as if that opening were the source of the wave. So here's your diagram. A small opening is, you know, there's going to be more bending of the waves, but it's treated as the new source. Don't leave yet. This also happens around corners. Fill in these blanks. The longer the wavelength, the more it will bend around a corner. So high-pitched sounds, like sounds from a trumpet or from a piccolo or from a violin or something like that, if you have a high-pitched sound, it's a little bit more direct, higher frequency. But the low bass sound from like a bass drum or a bass amplifier, those are longer waves, and those get pulled around corners a bit easier. So that's why when you hear like if a car is coming down the road and it's got a big stereo system, right? You hear the bass first. You always hear the bass coming first. That's because it'll travel around corners and permeate things here. Okay? So that's what this last section talks about, the thumping car bass. All right, that's it for chapter 11. Please take a look at the website for questions. Here's your questions here for chapter 11. Get a start on those questions tonight. You should do the first few if you can. 3 or 4 tonight. That's your homework. See you tomorrow.